Welcome to The Explainer. Today, we are diving into a really cool experiment that takes the super weird rules of quantum physics and stretches them to their biggest limit yet.
You know, in our everyday world, the answer is a big, obvious no, right? My coffee cup is on my desk and only on my desk. But what if I told you that in the quantum realm, the tiny particles that make up that very cup can actually exist in many places all at the same time? Now, you've probably heard of the most famous example of this weirdness, Schrödinger's cat. It's a thought experiment. But the idea is that a cat, locked in a box with a quantum trigger, is somehow both alive and dead at the same time, until we open the box and look. And that right there, that's the huge puzzle. We live in a world that follows classical common sense rules. But the tiny world of atoms and particles, it plays by a completely different set of quantum rules, where being in a superposition of many states at once is just normal. This leads to one of the biggest questions in all of physics. I mean, how big can something get before it's forced to play by our rules? Before it has to pick a side, stop being a quantum wave, and just be a normal classical object? Scientists have been pushing at this boundary for a long, long time.
And that brings us to the new heavyweight champion of the quantum world. So, in a truly landmark experiment, physicists took a sodium nanoparticle, and this thing had a mass of over 170,000 daltons. A dalton, by the way, is just the unit scientists use to measure the mass of atoms.
And we're not talking about a single atom here, not by a long shot. This is a tiny, nanometer-sized piece of metal. It's a cluster of more than 7,000 sodium atoms all stuck together.
Just to put this in perspective, this little cluster is actually more massive than things like antibodies in our own bodies. The goal of the experiment was to see if this entire object, all 7,000 atoms, could be delocalized, basically smeared out like a wave over a distance more than 10 times its own physical size.
Okay, so you have this giant nanoparticle. How in the world do you actually test if it's acting like a wave? Well, you build a very, very precise obstacle course for it, and you see what comes out the other side.
And here it is. This is the setup, called the muscle experiment. At its heart is something called a Talbot-Low interferometer. Now, this doesn't use physical walls or slits. Instead, it uses three perfectly spaced gratings that are actually made of intense ultraviolet light. Here's the play-by-play of how it works. First, they fire a beam of these nanoparticles. The first laser grating kind of preps the particle, splitting its wave-like self. The second grating then directs those waves. And finally, the third grating acts like a stencil, which lets the scientists see the exact pattern that emerges on their detector.
So, why go to all this trouble? Well, they're looking for a very specific result, a kind of quantum fingerprint.
It all boils down to this one question. After going through that whole obstacle course, does the nanoparticle show up at the detector like a tiny little rock? Or does it show up like a wave that has passed through and interfered with itself?
The predictions here couldn't be more different. If our classical, everyday physics holds up, the particles would just land in a kind of fuzzy blob. But if quantum mechanics is right, the particle's own wave would interfere with itself, creating this really distinct pattern of bright and dark stripes.
And this is what they saw. A clear, unmistakable interference pattern. This, right here, is the smoking gun. It is proof that each one of those huge 7,000-atom nanoparticles traveled through the light gratings in multiple places at the exact same time, behaving as one single massive quantum wave.
I love how the researchers put it in their paper. They basically said they took something that seems completely impossible from our everyday point of view and turned it into a measured experimental fact. Now, this isn't just some neat trick in a lab. This is a huge deal. It's a massive leap forward that absolutely shatters a key record in physics.
Physicists actually have a way to score these kinds of experiments. It's a measure called macroscopicity. You can think of it like a high score for quantum weirdness. It's a single number that tells you just how far you've pushed an object into the quantum realm.
And to really get how big of an achievement this is, just look at the jump. For years, experiments with bigger and bigger molecules had been slowly inching this score upwards. This new experiment just blew the old record completely out of the water.
The final score came in at 15.5. The previous record was about 1.5. So this isn't just a little bit better. It is a full order of magnitude better. That means 10 times better. It is, without a doubt, the most rigorous test of quantum mechanics ever done at this kind of massive scale.
So if quantum mechanics still works for a 7,000-atom chunk of metal, what's next? Where do we go from here?
And this, for me, is where things get really wild. The technology they developed for this experiment means they can start thinking about putting even more complex things into a quantum superposition. The mass they've already achieved is in the same ballpark as large proteins, and it's getting close to the mass of small viruses. The next frontier could literally be testing the quantum nature of life itself.
Research like this really confirms that the line between our familiar world and that bizarre quantum realm is so much blurrier than we ever thought. It forces us to ask, if something this big can be in two places at once, what other basic ideas about reality are just waiting for us to test them?